Okay, here's the graph of the original function. F of x equals x to the fourth minus 8x squared plus 10. It looks like at 0, 10, we have a relative or local maximum. And at -2, -6, and 2, -6, we have local minimums. What does it mean to use the second derivative test to locate those values? So I've got the first derivative here, 4x cubed minus 16x. And if we set that equal to 0 and solve for x, we will have identified what are called the critical numbers for this function. I can factor out of 4x and get x squared minus 4. Set each factor equal to 0 using this zero product property. So this factor gives me x equals 0. If x squared minus 4 equals 0, x equals plus or minus 2. So those are your three critical numbers. Now realize at this point we could use the first derivative test to identify the local maximums and minimums. We could put -2, 0, and 2 on a number line and identify whether the first derivative is positive or negative in the intervals created by those critical numbers. For example, if I put -3 into f prime, we find out that we've got a negative number, which tells us that the original function is decreasing. And I'll just draw the rest of these arrows here. This is positive, negative, positive. So the fact that the function goes from decreasing to increasing at -2 tells us that -2 is a local minimum. And likewise at 0, we have a local maximum. But we're supposed to use the second derivative test, which means we find f double prime, which gives us 12x squared minus 16. Now, there's two uses for the second derivative as far as graphing functions goes. We can use it to test for concavity, and we can use the second derivative to identify local maximums and minimums. If I find f double prime of -2, for example, that means put -2 in to the f double prime function. I'll get 12 times 4 is 48 minus 16 is 32. I don't really care what the value is. I just care that it's positive. And that means at this location where this -2 occurs, the curve positive, think smiley face, concave upward, which means the tangent lines are below the graph, but the point is -2 is on this concave upward portion of the curve. It has to be a local minimum. So we could put -2 back into the original function, find f of -2, and I'm sure you'll get -6. Similarly, f double prime of 0, the other critical number, gives us a negative value. -16 is less than 0. Think negative, frown, concave downward. That means 0. At 0, we have a relative maximum. And f of 0 gives us 10. Put 0 in for this x. And I won't go through this, but f double prime of 2 works just like f double prime of -2. Okay, so that's the second derivative test. It is not the test for concavity. We could find points of inflection and test for concavity by putting the places where the second derivative is equal to 0, which would be, well, x squared equals 16/12 or 4/3. So at x equals plus or minus 2 over the square root of 3, or 2 radical 3 over 3. There are points of inflection. Well, we'd have to test it to see if the concavity changed, but it looks like it does, like probably right here and right here. It changes from concave upward to concave downward. So that's the test for concavity. It is not the same as the second derivative test, which requires you to substitute the critical numbers from f prime into the second derivative to determine the sign of the second derivative, positive or negative, and that will tell you whether you have a relative maximum or not. And by the way, if you substitute a critical number into the second derivative and get an answer of 0, you have to fall back to the first derivative test. Okay, there you go. Hope that helped. Have any questions, post a comment.